We'll go ahead with today's class. So let's put it this way. Okay, and then Control L. Okay, are you able to see the screen?
Yes, sir.
Yes,
Okay.
sir.
Yeah. So okay, we'll move our discussions to the concept of entropy. We are done with the first law, or whatever we should have covered. We have done that pretty uh, exhaustively. We'll go a little fast from here on. Okay. Now, so yeah, to begin the discussions, we'll maybe take a update of what all you know about spontaneous processes and non-spontaneous processes. You know, I think you guys know that natural processes are spontaneous process, right? Like some of the examples are given here. Like if you open a container of gas into a vacuum, it immediately expands onto that, sort of fills the vacuum space from the gas that is connected to it. And you don't have to do something. It almost automatically or naturally it happens, right? And like that, if you keep a hotter body outside and expose it to temperature, when you say hotter body, that means that the temperature outside, which temperature in the atmosphere, is going to be lower. So if you take 25 degrees Celsius atmosphere temperature, and then you have a body which is at 50, and you just leave it like that, and eventually that one gets cooler. You don't have to do much. It automatically it gets cooler. And there are so many examples for that, like falling off an apple, running of water through a stream. The thing is that you don't have to do much, and it just on its own, it happens. And it's very spontaneously happens. These are the natural processes, and these are called spontaneous processes. On the other hand, if you just talk about the reverse of that, right? And if you open up a balloon sort of uh, enclosure, or the plastic or the polymer enclosure, the balloon doesn't really automatically gets filled up. Okay. Neither you put something inside the refrigerator and that doesn't get cooler than the atmosphere unless you plug it into the power. Okay, unless you supply something, it doesn't automatically gets cooler. Likewise, there are several examples of that. Uh, one being water doesn't actually split up into hydrogen and oxygen on by itself. You've got to do something to be able to do that. I'm not saying that these cannot happen, but this can happen not naturally. You artificially do that. For that, you need to, in a thermodynamic principle, you need to apply some energy onto that. That's how it is going to be possible. Those are not natural processes. And the question then becomes, what is it that drives the natural processes? All right. So uh, there are several uh, arguments we can put forward to as to why it happens. Okay. The question is, can it be the minimization of the total energy of the system, which is something we at some point were prompted to think about. That's partly true, but that's not entirely true, right? Partly true, meaning that it's one form of energy, or an algebraic sum of the all available energies that has to be minimized, but that we haven't gone there yet. When we talk about energy, currently we are thinking about either internal energy or enthalpy. All right. And if we think that for natural processes to happen, which direction the process would go to, is it the direction that it's going forward to energy minimization? With the current understanding of our energy, it's not, because the idea is that the total energy must always stay constant. That's what the first law says. It's a universal law that energy cannot be created. It has to be conserved all the time. And is it the total energy of the system, either one part of energy or the total energy of the system? But again, in the current understanding of total energy, it's not entirely that. A simple example is given. Think about a gas expanding into a vacuum, and that process, let's say if you consider that it's an isothermal process. Even if you consider in an isothermal process, expansion of a perfect gas into vacuum, that happens. That's a natural process. It happens spontaneously. That means we can try and test this argument of energy minimization. Okay, if energy minimization is true. But then that's not quite true, because when you continue this process of expansion in an isothermal mode, then what's the change in internal energy? The internal energy doesn't change because it's no temperature change. So the energy change in the system is pretty much the same, yet the process is spontaneous. So what is it that drives the the spontaneity of any processes that happens spontaneously? Turns out it's the distribution of energy in the process. You know, you guys might be used to the thing called orderness or disordernness in a system. But let me put it in a slightly different perspective, because that's perspective we already. Yeah. Anyone saying something? Yeah. Yeah, unless you want to speak, please mute your microphone so that we don't get derailed. So yeah, the point that I was coming to is it's about the distribution of energy in the process, right? Natural processes would always like to spread the energy out. That's the process. And there sort of this again is sort of a process here in this on the left. Here you drop a ball and sort of bounces back and forth and all that, and then gradually it comes to rest. So the ball was at this height, and then you drop it, and then it sort of makes bounces and all that, comes to the floor, and that's where it is stable. But then if you talk about the reverse process of it, okay, here the energy is released here. Now, if you think about another process where you get the ball, you keep the ball on a surface which is, let's say, hotter, like because you want to put some energy, you want to give energy to the body so that it actually bounce back. But then, even if you put energy to the body, does it bounce back? No, it doesn't, because all the motions are here are uncoordinated. It's if it is the hotter one, there's a thermal vibration that's happening in the body here and here also. When it comes in contact with the hotter body, there are also vibrations happening, and but those vibrations are in an uncoordinated way, so that it sort of cancel out each other, and then it sort of doesn't go up. For this to go up, what has to happen is all the molecules, the particles of this body, has to all of those particles have to move in tandem in this direction, so that this has to sort of go up. This is naturally happening, and this is not a natural process, right? And why this cannot happen, we'll understand that. So to bring in the context, let's go back to our earlier diagram of pressure volume work. Well, this we have spoken about in the first law of thermodynamics. So here we had identified two processes, right? So there's a perfectly reversible process, and there is something like an irreversible process, right? So if you say this is the initial coordinates of thermodynamic coordinates, which is here in this diagram, pressure and volume, and this initial coordinate is that this pi vi, and this final coordinates are pf and vf, and you can come from this point to this point in many different ways. Several ways you can come about. Turns out the best way to derive work and come from this initial position to final position is a reversible process, right? And this process, how do you go about, is that you take a smooth curve out of here from this point to this point, and you move in extremely slow processes, okay, infinitesimal small steps throughout this thermodynamic space, where you can at one point you can go back there, or you can continue forward motion without actually aiding any other energy. Okay, and this is a process which gives you the total work that you can calculate, right? That's NRTLN VF by VI. That's the work. You can look at the formula. But there are ways where you can do this work almost instantly, or rather in a fast manner. All right, and the let's say the quickest way would be to simply come from PI to PF and letting the expansion happen from here to here. Right. So these are the two steps that are given. Here you go like this, or you go like this. Okay. But there are places in between where you can come from PI to PF through, let's say, 5 different changes in pressure. Like you start from here and then you come here and you come like this. I wish I had a pen I could write, but then I think if you mark the cursor movement, you can sort of understand. So it might so happen from here to here if I have to come, and then from VF to VI to VF if I have to come, I can come through 5 different steps, or 5 steps, let's say. And how do I come? Like I come from here to here, and then you go like this, and then you from a little smaller, and then you go like this, and a little smaller, you go like this, and one more, you come like here, and then you come like this. All right. So if I take 5 different steps, then you'll see the 5 notches here. You'll see 5 notches here through which the process happens from PI to PF and then VI to VF. If you do it in one shot, it just comes like this. But if you do it in 5,000 shots, then you'll come like this. You'll see a tooth kind of curve like this. But if you do it in 5 lakh shots, then it will almost appear that you are in an infinitesimally small steps you're moving, and then you're moving from PI-VI to PF-VF. All right. So these are the various ways with which you can actually transfer the process, or transfer from PI-VI to PF-VF. And accordingly, there's a different amounts of works that you can do. All right. The best work that you can do is that in the reversible process, like the formula you have, the work W is nRT ln V2 by V1 or VF by VI. But any other processes that you take, that's going to be a slightly smaller amount of work that will be able to do. So this is the final the most common way of getting that work done, where you suddenly drop from PI to PF, and then again the VI to VF is drop. All right, so if you do like that, you'll be able to do only this much of work. But if you do infinitesimally small process, like we talked about in a reversible manner, then you'll get the work which is like this. So the point is that there are depending on the ways that you do the process, you derive the amount of work, right? If you do a perfectly reversible manner, if you conduct the process in a perfectly reversible manner, you'll be able to derive the maximum work out of it. If you do it very suddenly, then the work that is you obtain is about this much. Okay, I would like to. It's a very bad example that I'm going to give right now, but then it sort of makes sense. Compare the batting abilities or qualities or characteristics between Sachin Tendulkar and Virendra Sehwag. All right, Sachin Tendulkar is so much in control that he can actually take 4 shots out of the same delivery. Virendra Sehwag is already committed, and then he does things in a flash. But in the process, if you look at the lifetime of scores that they have made, the average of Sachin Tendulkar is much higher than what Sehwag has made. So I'd like to say that this is the first abrupt, impulsive kind of thing that Sehwag does, not so reversible process, does things immediately, but then the output is not the maximum. We'll talk about the reversible reaction. It's the Tendulkar process where things are optimized and then it gives you the best output, right? So that's the difference. Now, let's say in this discussion, uh, we have been able to differentiate between the best processes, this best process, and the one that is not so best process, and there are something in between also. Like if I have to carry the experiments or the transition from PI VI to PF VF in 10 different steps or in 20 different steps or 100 different steps, then the work output is going to be slightly different from each other. Now, if that there are so much of differences between this completely reversible process and then the irreversible process, then there has to be some measurement which will quantify as to how much irreversible the process is. All right, please get this thing in your mind. There's the best process, the best practice, and there's this not so best practice, and there is something in between. There are practices which are not, which are better than the worst, but they're not as good as the best one. And there can be various different steps, various different ways that you can conduct the whole process. And if that is so, then there has to be some kind of a measurement. There has to be some quantification of the degree of irreversibility. That's what I mean by the degradation of work. You had the best work here, but then in this process, your work is degraded. Okay, and if that is so, then there has to be some measurement of the degradation of work, right? And that's where the concept of entropy is coming in. Right? So entropy is that aspect which actually would measure the degree of irreversibility in a process. Right? And you guys are all you guys always think that entropy is sort of connected to disorderness or orderness. It's perfectly fine. It's absolutely fine. And you don't have to bring about a change in the thought process. But on top of that, I think you should start thinking about one more aspect, and that is the dispersal of energy. And a process which actually goes for distributing energy. Like say, if you have a lot of money, then the natural tendency of money is to be distributed. You have to actually do something to keep the money with yourself, right? Those are bad examples that I'm giving, but then I think it will help you understand what I'm trying to say. So it's the entropy is of course connected to orderness and orderness or disorder, and it's at the same time it's connected to the dispersal of energy, to the distribution of energy. Right? In that sense, when it distributes, the entropy is sort of going up. Okay. Okay, so we'll go with a simple understanding of entropy as the parameter that measures the degree of irreversibility. It will quantify how irreversible the process has been followed. Now, if you go back to the same thing, you can actually do no work by expanding it into vacuum. Vacuum is what? What the pressure is? Zero pressure, right? That means you are bringing from here to here. Pressure is zero. That means what is available work then? Only this much. Only a straight line. And straight line means area is zero. That means if you expand the whole thing into vacuum, there is no work done. That is a worst sort of worst reversible process. It's completely irreversible process. All right. But if you just leave it to just a little bit of pressure, and then you do the process, then you'll be available with this much of work only, which is extremely small amount of work. So that in that sense, you'll say that the degree of irreversibility is almost 99%. Right. So that's the measure that we are talking about, and entropy is something which help us understand that. And entropy is a function of state. That means it depends on the initial and final coordinates or intermediate. It actually doesn't really depend on the intermediate coordinates in the process. And if you do the process in a complete cyclical way, then it starts with the initial thermodynamic coordinates, and then and go about many other thermodynamic coordinates, and then come back to the initial one. And in the whole process, which is a cyclic process, the entropy change is going to be zero. It's no change in entropy in that sense. And this can be expressed in with the three basic thermodynamic parameters, PV and T. And that's why it's a function of S is a function of PV and T. And in a functional mathematical relationship, it's simply the degree. I'm sorry, the heat exchanged in a reversible manner, in a reversible process. So the reversible heat, sometimes called that, or many times called the reversible heat. The reversible heat normalized by the temperature. That's the basic mathematical formulation. And then you like to track the whole change of entropy in a process from I to F. That'll be this infinitesimal change in the reversible heat divided by T, and that has to be integrated over the initial coordinates to the final coordinates. So that is what gives you del S. Right? And can anyone tell me who is this scientist? Anyone? There is a clue, but then I don't know if you can get that. Yeah. Is anyone saying anything? Or someone is in the market? Yeah. So this is a scientist. This is an Austrian physicist. All right. And this is his tombstone. The picture that's here, it's the picture of his tombstone. All right. There's a bust of this great person. What I want you to see is what is written in the back. Okay. S is K log W. And this is the most famous equation he derived, he gave it to the world. Yeah, that's right. It's Ludwig Boltzmann, right? And such a wonderful person, or he didn't do the epitaph or the tombstone, but then people did. And after he passed away, people wrote his most famous formula in his in a graveyard, in his grave. So this is Ludwig Boltzmann, and the formula that you see is one of the most famous formula that would define entropy, right? So S is K ln W, or sometimes we write it omega as well. So many of the books you'll find this, but then I thought we should write W because it's there, officially there in his tombstone, right? So this is entropy, and what it says is that this W is the number of microstates in a material, right? And what is W? Then what do you mean by number of microstates? It means the number of ways in which the molecule of a system can be arranged, right? While the energy must remain constant, right? Within the same energy, how different ways that you can actually fill all the molecules in the various energy levels. Now, when you talk about a temperature, there are various energy levels for a system, right? And the molecules have to occupy those various energy levels. The many energy levels, if there are there, then there are many ways you can actually fill those molecules in those energy levels, which tells us that entropy has to be positive. Look at the mathematics of it. If W is 1, if there is only one microstate available, that means the molecules only can fill that microstate. That means there is no entropy, because if W is 1, then natural logarithm of W is going to be 0, and the entropy is 0. But that's not possible. There are many microstates always. There are always more than one microstate for any material that you talk about. When there is a positive temperature, it's mathematically you can prove there are many microstates. If there are many microstates, then W is more than 1. If W is more than 1, then S is going to be more than 0. That means there is always a positive entropy uh, anywhere in the world. So any material in isolation that you talk about. Okay. So that would say that this is a very profound statement. A more disorderly distribution of energy and matter corresponds to greater number of microstates associated with the same total energy. Okay. Now we are considering the total energy remains the same, but then if you have more disorderly distribution of energy, then that corresponds to greater number of microstates. And if there are greater number of microstates, correspondingly entropy is going to be much larger. Okay, the whole this concept of this approach of understanding uh, entropy is called statistical mechanics. We call it statistical physics as well, statistical physics or statistical mechanics. Right. So we are not going to go much deeper into that, but then it's very useful for us to actually keep this formula in mind. It sort of would explain much of the things in a very simplistic manner. Right. So okay, now yeah. So if that is said, let's go back again. Like if that is so, then let's bring a contrast between what are the number of microstates available in a solid system and what's things in a liquid system and in a gaseous system. And you naturally see that the number of ways that energies can be distributed in the system in a solid is rather limited. The molecules, the atoms and molecules are kind of with fixed positions, and then they don't change too much other than vibrating about a main position. So the number of ways you can actually distribute energy within a solid is not many. On the contrary, if you look at the liquids have only small units which stay constant, right? But then there are several ways that you can move about, and you look at the total ways that you can distribute energy in the liquid, it's much higher in the sense, much higher compared to what can be done in a solid. And likewise, a gaseous state would have much more number of ways of distributing energy. In that sense, you would see that the absolute entropy, when we calculate that, uh, it's much lower for a solid system, and for a liquid, it's higher than a solid, and then for the gaseous system, it's much larger, and then certainly larger than the liquids and the solids. Right. So these are some of the functional relationship of entropy with other parameters, or what happens when the changes in a process, in different processes. And if you like to find out what's the change of entropy in a reversible isothermal process, it is simple. If you oh did this is wrong. This is wrong. This has to be by T, isn't it? Yeah, please make sure we sort of note that. So del S in a reversible process is QR by T. It doesn't have to be a reversible process, but then well, I'm sorry, not it doesn't have to be an isothermal process, but del S is always QR by T. T is missing here. And if you talk about the isothermal process and apply the first law of thermodynamics, then you'll find that the Q, the reversible Q, is equivalent to only the work done, because du, the change in internal energy, is 0. So if that is W, that means it is dV, and then you put instead of P, nRT, then you get the number nRT ln V2 by V1, and since del S is going to be QR by T, That means W by T, then it's going to be NR ln V2 by V1. Here it is by T and here it is by T missing. Okay. So the del S, if when W is nRT ln V2 by V1, del S for the isothermal reversible process is going to be NR ln V2 by V1. It's just simply the T goes away. And one more thing that we should consider here is that what happens, entropy changes, with temperature, it's generally continuous, goes with a smooth curve and all that. But it's discontinuous at the point where there is a phase change. If you look at the entropy curves of any material and how does it change over temperature, you will find that there are several places or some places where there is a discontinuity. It sort of leaves there and then starts from elsewhere. What is that? That means there is a phase change, right? And what is a phase change meaning? What? That's an isothermal process again, right? Because the temperature doesn't change, but there is a heat change. Okay, and the heat change is simply the change, the enthalpy of phase transformation, phase change enthalpy, or sometimes call it latent heat of phase change. If it is solid to liquid, it's latent heat of melting, and for liquid to gases, it's latent heat of vaporization. So that's the enthalpy that is involved. And that enthalpy change, that's the reversible heat change, and that is happening at the transformation temperature. So it's the melting temperature for the solid to liquid transition. It's the boiling point for the liquid to, I'm sorry, is it the boiling point? Yeah, it's the boiling point for the liquid to vapor transformation, right? So if you have to calculate the entropy change due to a phase change, then you simply have to do is the del H of phase change, which is the latent heat of the particular phase change that you're talking about, divided by the transformation temperature. That gives you simply a del S quantity, and this del S quantity is the quantity which is the difference between in the discontinuity. Like say if a S curve is like this, mark the cursor. If the S curve is like this, and this point it sort of stops and then starts from here and goes like this. So this is for the solid and this is for the liquid, and the discontinuity here is actually going to be the del S for phase change, right? And that's a positive. That's a positive because see, if you're going from a solid state to a liquid state, you're actually putting more and more entropy. That's going to be more disorder. There's going to be more number of ways, more distribution of energy is possible. That's the region where it jumps by a certain number from the solid melting point and the starting of the liquid entropy curve. All right. Likewise, you can put various relationships with different forms of energies, and here we'll talk about how is it related to internal energy and how is it related to enthalpy. Those are the two most common energy forms that we have. And this is universal. ds is dq by t. And from taking this relationship, when we go to the first law of thermodynamics, which is dq, this has to be a capital Q, like according to our convention. This dq is du plus pdv, that's the first law. And dq from this reaction, from this relationship, you know that this is TdS, right? Now, so du is going to be TdS minus pdv. So from this, you can get this functional relationships, which is del u by del S at constant volume. Del u by del S at constant volume is going to be T. That means del u by del S, and if you do it as constant volume, it's going to be T. Likewise, del u by del V at a constant entropy, you get minus S. These are the functional relationships. Likewise, and these are going to be useful much later, when we talk about auxiliary functions and the various functional relationships between, all the other thermodynamic quantities that we have. And there has to be mutual relationships, and then to simplify that, we need these relationships. And of course, when we study Maxwell relationships, these are going to be useful. So that's the relationship with internal energy. Uh, Likewise, we can establish how does it look compared to enthalpy. And you know that enthalpy dH is du plus pdv plus vdp. Where does it come from? Now, you know that H is u plus pv, and then you take a differential form of that, and that is dH is du plus pdv plus vdp. So pv is differentiated here. Right? And then you see that du plus pdv, according to the first law, you can write that as dq. Right? So this becomes then dH is dq plus pdv that's coming up. And this dq is by definition is TdS, because that's the basic definition of entropy. So instead of dq, if you write TdS, then dH becomes TdS plus VdP. This is also a very important relationship in thermodynamics. dH is TdS plus VdP. So if that were so, then excuse me, then del H by del S is going to be T, temperature, simply temperature. Okay, and del H by del P is going to be V. Okay, so if you look at these two relationships, del U by del S and del H by del S. So del U by del S is at constant volume is going to be T. Okay. And del H by del S at constant pressure is going to be T. That's the sort of relationship between energy, two different energies, and how do they relate, how do they compare with entropy, right? And likewise, you can figure out how does entropy behave in relations with temperature. That's an extremely important one. As I told you that the S curve kind of rises with temperature. It's very intuitive to understand that when your temperature is going up, you can see that there are more and more microstates are being available for the molecules to get filled. So that means you have more choices for you. That means the many ways that you can actually, within the same energy, in many ways you can fill those energy levels. That'll tell you that entropy is going to increase when the temperature sort of goes up. But then I think in the earlier classes we had talked about that entropy has a steep increase till about certain temperature, and post that it's only a subtle, very gradual increase. The slope is fairly low. But then at this point, it's very important for us to understand how sort of changes in a constant volume process and in a constant pressure process also. And you know that constant volume process has some sort of relationship with the internal energy part. And we talk about constant pressure process, it's always related to the enthalpy part. We'll see how it is, So dq is du plus pdv. That's from the first law. And you know that du is cv dt. That's the definition of cv that we got. So du is cv dt and then plus pdv. So if you simply do ds by dt at constant volume is going to be cv by t, and then take a del S or the entropy change in a constant volume process over a certain temperature range. That's T1 by T2 Cv dt by T, which is what giving you Cv ln T2 by T1, right? Likewise, you could see that you could write dq is TdS, and TdS is simply dH minus VdP. Okay, if dH minus VdP, you can simply write dH is Cp dt, and this Cp dt minus VdP, and then you can find out that del S by del T at constant pressure is Cp by T, much like del S by del T at constant volume is Cv by T. So if you take the pressure, the entropy change from temperature 1 to temperature 2, it's going to be Cp integral dt by T, which is Cp ln T2 by T1. So you'd see that it's kind of interesting sort of combination of properties here. You talk about the entropy change in a constant volume process. It is simply related to CV, logarithm of T2 by T1. We talk about entropy change in a constant pressure process is Cp ln T2 by T1. Or simply you can write that ds at constant pressure is Cp d ln T. They want to sort of integrate over that. Sometimes we write integral Cp d ln T instead of dt by T. We write simply d ln T. The same thing in here. So this is related, and the commonality is that in a constant volume process, you sort of relate to Cv or internal energy, and the constant pressure process we talk about Cp and enthalpy, right? So that brings us to formulation of the second law, which is essentially telling that with regards to entropy, and the various forms of the second law. I've listed only 2 or 3. There are statements by Planck, there's a statement by Clausius, and there are statements by Kelvin, and there's another statement by the Cara-Theodori. So many. This is a philosophical argument. There are many corollaries that will come about, and some of these corollaries are actually taken as, also said as the second law itself. But then we have simply made it. We'll keep it as simple as possible, and 3 formulations I've made, and these are actually representative of many of the formulations that you have for the second law. Entropy S is defined by the equation ds dq by T, dq reversible heat, is a function of state, right? And the entropy of an adiabatic system can never decrease. It increases in an irreversible process and remains the same in a reversible process. So that's fixed. So ds over a certain process is going to be greater than or equal to 0. Okay, it can never be negative, right? So if it is a completely reversible process, then ds is going to be 0. There's no change in the entropy of the system. If it's an irreversible process, then it's going to be entropy increases. The final entropy minus the initial entropy is going to be positive quantity. So that's what happens. That's for a natural process. Okay. Another formulation that's by Kelvin is that no process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion to work. Okay. You absorb heat and completely convert into work. That's not going to be possible. That's what is called a perpetual motion machine, the second kind. Okay, we talk about the perpetual motion machine, the first kind. That means there we talked about a machine which will take nothing from outside and always keep producing work. No, that's not going to be possible. Okay, here it is said that you cannot completely convert the heat that is supplied to a system and then convert it to work. You have to reject some heat somewhere, and that's the basis for the temperature scale, and that's the basis for finding out the efficiency of a process, efficiency of an engine. But then that's a lot of mechanical engineering onto that. We'll cover some of the aspects in the next class. But we're not going to go into Stirling engine or diesel engine or things like that. We'll talk about only the Carnot engine, and just take the ideas of efficiency, and then how do you sort of increase the work output and by just the temperature method, right? So this is where we'll keep it today. We'll go to the next one tomorrow maybe. Okay, so let me stop the recordings, and then we'll sort of take some questions.